Let's do an example of an ideal gas inside of a piston and represent it via a PV diagram. So we have a sealed piston full of an ideal gas. It starts so that the lid is pulled up and held by a locking pin such that the pressure is half of the atmospheric pressure. The piston is allowed to equilibrate to atmospheric pressure. The sense is that we've pulled out the pin so that it equilibrates. During this time, the volume halves. Draw the results on a PV diagram. How does the final temperature depend on the initial temperature? So first we should gather information. The first thing we need to look at is see that we have a sealed piston. If it's sealed, that means molecules can't come in and out of the piston, and that means that the number of molecules is constant. Second, it says we have an ideal gas in the piston, so we can use the ideal gas law. Further, we have information about the pressure. So it starts at a pressure that's half that of atmospheric pressure, so we can assume it's 0.5 atm. We can convert that into pascals. That gives us 5 times 10 to the 4th pascals. We can see that the final pressure after equilibration is equal to the atmospheric pressure. That means it's 1 atm or 10 to the 5th pascals. Interestingly, we can see that pressure 2 is actually just equal to 2 times pressure 1, and sometimes just using these types of ratios between the initial and the final states will actually be enough information to give us what we need in the problem. And it also says during this time the volume halves, so that means that V2 is 1/2 of V1. Let's see, we can organize our approach, so we can use the ideal gas law for both states. So for state 1 we get P1V1 equals nRT1, and for state 2 we get P2V2 equals nRT2. We also remember from above that V2 is equal to 1/2 of V1, and P2 is equal to 2 times P1. When we plug these into the ideal gas law for equation 2, we can see that you can plug in the numbers for P1 and V1, and that is equal to T2. Now we can analyze. So P2V2 is equal to 2P1 times 1/2 V1, which is equal to P1V1. P1V1 is by definition equal to nRT1, and P2V2 is equal to nRT2. That implies that T1 is equal to T2. So this means that the temperature before and after did not actually change for this piston. If we draw this on a PV diagram, we can start with our volume being the larger volume, V, and our pressure being 1/2 atm. Then the second location, or the second state, P2V2, is actually equal to the volume of V over 2 and the pressure being 1 atmosphere. And again, for both of these cases, the temperature initial and the temperature final is the same. Now there's a number of ways that we could get from the first state to the second state, but in the case of this, it actually has the impression that it's equilibrating slowly enough over time, which implies that the path from state 1 to state 2 is probably also at constant temperature the whole time. In particular, it implies that the piston is in thermal contact with a giant reservoir, perhaps just the air molecules outside, that it can exchange heat with while it's doing this process, and so that the temperature can actually maintain and be stable. If this is the case, if T1 is T2 for all time, so not the final T2, but anywhere along the path from T1 to T2, then that implies that this P1V1 is equal to P2V2 anywhere along the path. We can then write an equation that's more general and say that the pressure as a function of volume is equal to the initial state, pressure P1 and volume V1, divided by the volume at any location along the path between 1 and 2. So that implies that P is inversely proportional to the velocity. If this is the case, we can actually draw that state, and you can see that it goes not directly or straight across the hypotenuse, but it actually decays like 1 over V between V1 and V2.